Hey guys, this is AS Organic and we're doing optical isomerism. In the last video, we talked about stereoisomerism having two types of forms, cis-trans isomerism and optical isomerism. Just like cis-trans isomerism had some conditions, for optical isomerism for optical isomers to form, I also have some conditions, and I've divided the formation of optical isomerism into three different steps. So, the first step in forming optical isomers is identifying the chiral carbon. Suppose I have this big organic compound right here, right? And if I have chiral carbons, then I will have optical isomers. Now, what is a chiral carbon? For chiral carbons, always remember that they must have two conditions, and if both are obeyed, they are chiral carbon, and if they are chiral carbon, then again they are optical isomers. So, for chiral carbons to exist, they must be bonded to different atoms, right? So, let's see if these carbons obey this rule. I have three carbons right here, 1, 2, 3, and you can see that this carbon is bonded to three same atoms. It's bonded to three hydrogens, and that does not obey the first rule. This carbon right here and the center carbon obeys this rule because both of these are bonded to different atoms or groups. This carbon right here is bonded to a hydrogen, an alcohol group, and this alkyl group right here, and a carboxylic acid group right here. Whereas this carbon, which is bonded to an oxygen, an alcohol group, and this entire group right here. So this entire group is considered as one group, okay? So since all four are different groups, this also obeys the first rule. Now, the second rule is that carbons must have four single bonds. There must be no double bonds for chiral carbons to exist, right? So I can already cancel this out because it's not a chiral carbon. I'm only left with these two, and you can see that obviously this carbon right here has a double bond with oxygen. So this carbon doesn't obey the second law, and the only carbon I'm left is this carbon. Therefore, the center carbon is a chiral carbon. And if a chiral carbon exists in a compound, then I can use that chiral carbon to make optical isomers. Now, since I have a chiral carbon, right, the next step in forming optical isomer is that I draw the 3D shape of chiral carbon as well as the groups bonded to the chiral carbon. What do I mean? Well, I have this chiral carbon, right? I can take this chiral carbon and then draw these four bonds, right? These four bonds, I can draw them in a 3D shape. This is the 3D shape, and keep in mind I can put any of the four bonds on anywhere on these lines. So what I would recommend is taking the biggest and the most complicated bond and placing it at the top. So I can place this anywhere. I can put it here, 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 or here. What I would do is place it at the top because it's very confusing. So double bond O and then OH, right? And then this OH can be placed right here. This hydrogen, I'll place it right here. And this CH3 group will come right here, CH3. So I can write it like this as well. There is no issue. I can write this C double bond OOH group like this CO2H. This is this is an acid group, right? So this is what I call a 3D shape. Now, the final step in forming an optical isomer is that I take the 3D image, which is this right here, and I draw the non-superimposable mirror image of the compound in its 3D shape. Well, what do I mean by this confusing sentence? Well, I drew this 3D shape, right? So I will make a imaginary mirror right here, and I would replicate this. I will simply take this and flip it so that the 3D compound that I draw right here is mirrored. What do I mean by mirrored? Let's take my hand for example. When I flip my hand, the image that I get right here is a mirror image of my hand. So whatever was on the left comes at the right. My thumb, which was originally at left, would now be at right. The smallest finger which was originally at the right, would now come at the left because it's mirrored. So what I'm trying to say is that whatever is at the left would come at the right, whatever is at the right would simply come at the left. So I draw my central carbon atom. Let's say this is the central carbon atom, right? This is the central carbon atom. And you can see that the top finger, the middle finger, is the same, because when I flip the mirror image, the center would not change. The center would remain the same. So I draw the top bond, and then the thing at my right would come and go toward my left. And then this bond, which was at the left, would come at the right. Now, CO2H was originally at the top, so it won't change. My CH3 was this right here. The OH, which was at the right, would come at the left. So OH right here. This bond should be towards the O, by the way. And then finally, the one which was at my left would come at my right. So hydrogen like this. So this is the mirrored image. And when I do this last step, I can call these two optical isomers of each other. Why? Because one, they have a chiral carbon, and two, they are non-superimposable. What do I mean by non-superimposable? My hand right here is non-superimposable. Why? Because when I flip my hand, when I mirror my hand, the image that I get is not the same as the original image. But let's say I take this water bottle, which is symmetrical. It's very symmetrical, right? And when I flip this, I get no change. This is said to be superimposable. Let's do some exercise now. Let's say that I've been asked to find out whether each of these three compounds will form optical isomers or not. And earlier I told you the 3 steps, so let's follow them. First step is to find out whether I have chiral carbons in each of these compounds. So obviously this one and this one cannot be chiral compounds because they have a double bond. And this one can also not be a chiral carbon because it has 3 identical groups bonded to it. So the only carbon left is this one right here. So this carbon is bonded to an alcohol, an alkyl group, a hydrogen, and this group right here, this one big group. So yeah, this is a chiral carbon. Now moving on to number 2, compound 2. This carbon has 2 identical chlorine groups, so it cannot be a chiral carbon. Can this be a chiral carbon? Well, looks like it can be, because look, chlorine, hydrogen, bromine, and this group right here, this separate group. So 4 different bonds. Yes, this is a chiral carbon. In this one, the first carbon cannot be a chiral carbon because it has 3 identical hydrogen groups. And then I can also say that this cannot be a chiral carbon because the double bond, I can see a double bond between carbon and oxygen. Now compound 3, I can obviously cancel this out and this carbon out because both have hydrogens, multiple hydrogens bonded to them, identical groups, therefore they cannot be chiral carbon. So this and this is not chiral carbons. Now this carbon right here, I can see a double bond between this carbon and oxygen, so I can obviously cancel this out as well. And the only carbon left is this one. The central carbon is bonded to a methyl group, actually 2 methyl groups, because one has bonds shown and one doesn't have bonds shown. So sometimes they would do like this and students would get confused. They will treat this and this as 2 different groups, but they're not. Both of them are methyl groups and they are identical. So I cannot consider this as a chiral carbon. Now since none of the 4 carbons are chiral, this compound right here cannot show optical isomerism. So I only have carbon 1 and 2 which can show optical isomerism. So step 2 is drawing the 3D shape around the chiral carbon. So I take this, I draw the 4 lines that I would usually, like this, one like this, and then another one like this. Yeah, I can draw it any way I want, but yeah, like this. And then I can place, so these are my four bonds. One, this alkyl group right here, this is the second bond, and then the third bond is this group right here, and then the fourth bond is the hydrogen. So since this is my biggest group, I would like to place it right here, and this is C2. So You know what, let me just draw it like the C double bond C. This one has a hydrogen, and then another hydrogen, and then this one has one hydrogen right here. 1 2 3 4, yeah. And then at the bottom, let me place the methyl group, this methyl group right here, and then I can place the H right here, the OH right here. Now in the next compound, I will do the same, this like this, yeah. And then, yeah, so the biggest group I have is this one right here. So it's carbon with a chlorine, bromine. You know what, let me do it in a simpler way. So I'd say carbon that has chlorine twice and bromine. I can also write it like this. And then bromine will come right here. I can place all of these anywhere I want. It's not important. The important thing is that I draw the mirror image correctly. Hydrogen will come here, chlorine comes here, so this chlorine will come here. Step 3 was to draw the mirror image of the 3D shape that I drew. So let me just rewrite this, right? So this can be written in a simpler way like this: CH2 with a double bond, CH2 with a double bond, and then, yeah, the hydrogen CH3OH, hydrogen CH3OH. So this can be also written like this. Compound A can be written like this. Now when I draw the mirror image of this for optical isomers, the one at the top, the bond at the top will remain the same. It won't change. That's the good thing about the top bonds. It doesn't change. So you can have the biggest bond at the top always. Now these two bonds will flip towards the left when I mirror this. So like this, and then something like this, yeah. And then hydrogen here and CH3 here, and then the bond at the left would flip towards the right. So something like this, and then OH. Wait, this should be, guys, this should be dotted, not straight. I should have wait, yeah, dotted like this. One bond should be dotted, and two bonds should be in line, and one bond should be like this weird shape. Okay, so this is the mirror image. And then for the second compound, which is this one right here, I can draw the mirror image right here. So carbon, and then the biggest bond, which is Cl2 twice with a Br, and then this will stay the same. Obviously these two shift towards the left, so I get this, and then like this. This will have a hydrogen, this will have chlorine, and then the bromine shift towards the right. So bromine, which is dotted, will be like this.